Hello, it's a new week and we're back with more CAPE physics. We'll be continuing our journey today looking at charged particles in an electric field. I'm Paul Bender. All right, CAPE unit, physics unit 2, charged particles in an electric field. And this is the first part of a two-part lesson on this concept of charged particles in an electric field. All right, in this lesson, you will learn to, you will learn to explain what is a field, because that's a concept, sometimes it's a new concept. You will state the characteristics of what is called a uniform electric field, and you will determine the magnitude and direction of the electric field strength of a uniform electric field. You will also solve problems with uniform electric field in practical situations, all right? So these are some of the things that we want, some concepts we want to get across to you that are very important in this topic area. All right, what are some of the things you should know? All right, when you come into a lesson, you must have some prior knowledge. You should know that voltage is equal to work done per unit charge. The potential difference, or the voltage between 2 points, is the work done to move 1 coulomb of charge from one point to another. You should also know that work is force times displacement, and you should also know that work done is equal to change in kinetic energy, and that's called the work energy theorem. So when you do work, when work is done, some amount of kinetic energy is gained. All right? Okay. So I want you to watch these 3 demonstrations that I'm going to do here. All right? First of all, this is a magnet, and I have on this card here a coin. All right? So I'm going to use the magnet, and I'm going to just put the magnet, and I just want you to watch. Well, everybody knows this. All right, let me do it again. This is something that you might have done thousands or hundreds of times. All right, that's that. And then now I have just a pen and some bits of paper on the same card. I'm going to rub the pen vigorously on my sleeve. And then I'm going to just hover the pen over the bits of paper, right? I'll do another one. Rub the pen. All right, there we go. All right, okay. And then thirdly, I just have a ball of tissue here, just a ball of tissue. I'm going to just drop it. That's it. All right, just drop it. That's it. So that's the demonstrations, 3 demonstrations that I have done. All right. I'm going to put 2 statements. I want you to say whether these statements are true or false. First one, no contact was made with any of the objects to make them move. No contact was made with them. And secondly, each of the objects experienced a force. All right? So, all right, let me go back. I think I have a problem here. All right. Here, each of the objects experience a force. Now, was contact made with any of the objects? No. What happened is that the magnet just hovered over the coin, and the coin moved. All right? And so if for the coin to move, it must experience a force. It was at rest, and then it went up to the magnet. So that means that it had to experience a force. And the same thing with the bits of paper. They were on the surface of the card, and when you put the charge pen over it, they experienced a force and they went up to the pen. Also, this ball of tissue was stationary, and when I released it, it fell towards the table. That means that if it accelerates, there must be a force acting on these objects. And so the question is, where did these forces come from? So let's see. So what is it that happened? What really happened in these three cases? I know that you might have been introduced to these forces and they call them action at a distance forces. All right, but we will look a little bit more into what it is that actually happened to make these objects move and experience that force. All right? So each of the objects experienced a force because they were in a field. They were in a field. I know when you watch the sci-fi movies and the different movies, they put a shield, a force field around themselves and that kind of stuff. But we have many fields that exist around us, all right? And so they were in a field. And so the question now arises, what is a field? All right, now this is a bit technical. It says a field is a physical quantity in space which an object with a physical characteristic that is compatible with the field can experience a force. So a field occupies space, all space around us. All right, we have many, many fields, and we will look at some of them, and they just occupy space. But if a particle, an object, has some physical characteristic that is compatible with the field, it can experience a force. So, for instance, if I put this magnet over these pieces of paper, then none of them get attracted to the magnet. However, the coin will, right? Because the coin has some physical characteristic that is compatible with the field produced by this magnet. And so it will be attracted to it, okay? And so that is what this is saying, all of this fancy language is saying in a nutshell. All right? So what were the fields present in the demonstration? We did a demonstration, 3 demonstrations. What were the fields that were present? We had, for the bit of paper, we had an electric field. When we rubbed the pen, when I rubbed the pen on my sleeve, the pen became charged. And because the pen became charged, an electric field developed around the pen. Now, once we put the pen and the field, these bits of paper got into the field produced by the charge on the pen, then they became charged, and as a result of that, they experienced a force. All right? Then you have the pin, or the coin. I had a pin originally, but I think that might have been too small. So the coin that was in a magnetic field, and we will see what physical characteristic that had. And then the tissue ball, it's in a gravitational field, and we're all in a gravitational field. Once we are on Earth, once we are on any planet, we are under the influence of a gravitational field. Okay, that's an all-compass. So what physical characteristic is compatible with the fields? So for an electric field, an object must have a charge in order to experience a force in an electric field. It must have a charge. If it doesn't have a charge, it cannot experience a force in an electric field. Okay? And then we have magnetic field, and these are just 2. An object must be what is called a ferromagnetic. It must have some derivative from iron, right? And it must have some property of iron, and that was called a ferromagnetic material, and that in that way the object would be able to be attracted or experience a force when it is in a magnetic field. Also, a charge which is moving in a magnetic field can experience a force. So not a stationary charge. A stationary charge would not experience a force in a magnetic field, but a charge which is in motion in a magnetic field can experience a force. And we wouldn't get into the fullness because it doesn't have to, but it can. All right? And then for the gravitational field, anything that has mass. So the bits of paper, if I pick up a bit of paper and I drop it, that will experience a force. As long as it has mass, the gravitational field will exert a force on it. And so we're saying that this field is a quantity in space in which anything that is compatible with it, that has some physical quantity that is property that is compatible with the field, it will or can experience a force. And so we want to, the field occupies all space in the region where it is. It doesn't occupy pockets of space, like you have a field here, piece of the field here, no field, and piece of the field. And we know that for gravity, right? It will be very disconcerting if you drive in or you're walking on the road and suddenly there is no gravitational field. So you go up in the air and then you feel gravitational field again and you get pulled down and so on, right? That we know as we walk and as we do our stuff, the gravitational field is there. It's all pervasive, okay? All right. So we will look at a specific type of field called a uniform electric field, all right? A specific type of field called a uniform electric field, right? Because we were looking at our topic area is charged particles in an electric field. And we will look specifically today at charged particles in a uniform electric field. So let's see what a uniform electric field is all about. All right, so the uniform electric field. A uniform electric field is produced when parallel plates of opposite charge are brought close to each other. And you see the electric field sweeping out. All here is the electric field. So all in between here is the electric field. But when we're going to represent it on paper, we can't draw lines on every space. So we represent the field by lines with arrowheads. And if you notice, the lines are evenly spaced, suggesting uniformity. So this is a uniform. So we have a plate that is positively charged and a plate that is negatively charged. And in between that, we will have an electric field, okay? All right. So charged particles of the same magnitude will experience the same constant force at whichever point in the uniform field they are placed. So if you place a charged particle here, it will experience a force and it will be caused to accelerate. If you put it there, this one is negative, it will experience a force and it will go across. Put it here and experience a force and it will move across. So wherever in the field, in a uniform field, you put a charged particle, it will experience a constant force which will cause it to accelerate. All right? And as if all the charges have the same magnitude, then they will all experience the same magnitude of force in the uniform electric field. Even though the force may be in opposite directions, as we saw with the negative charge here and the positive charges, all right? So they will experience the same constant force at whichever point in the uniform field they are placed. Okay, we will engage in a term called the field strength. How strong is the field? Field strength. How strong? Some fields are stronger than the other. Those of you who might have used magnets, you know some magnets stronger than the other. Some of them, you just put it and it kind of fenke. It can't even lift up nothing. And then some other ones, it lifts it up. It's stronger. The field has a greater strength than one field than the other. All right? And so the field strength of a uniform electric field is a vector quantity. That's the first thing. Field strength is a vector quantity. Okay? So that means it has magnitude and it has direction, a stated direction. And so if we are going to talk about field strength, we'll have to speak about its magnitude and its direction. All right? Okay. Its magnitude is defined as E. We use the symbol capital E for the field, and that is equal to the potential difference divided by the separation of the, right. So here we have V is potential difference and D is the separation of the plate. So if we connect a source of potential across the two plates, this one is positive and that one is negative, and the plates have a separation D, then, so here we have the potential and the plates, right? And so we have our uniform field. Okay, so this is how the magnitude of the field is determined. It is the potential difference across the plates divided by the separation of the plates. All right? Okay, so how do we determine the direction of a uniform electric field? So here again, the direction of electric field strength is the direction in which a positive test charge placed in the field would move, all right? So if you place a test charge, that test charge is moving diagonally. We place another one, that begins to move diagonally. So whichever direction, here we place another one, it moves diagonally. So wherever we place it, we find that the test charge begins to move diagonally. And so what we would say that the direction of the field is diagonally downward. And so we can draw our field lines downward like that. So that's the direction of the electric field. Because when we place the charge, it moves diagonally downwards. And so that tells us where our electric field is. All right? Okay. All right, so we're going to look on the force on a charge in an electric field, in a uniform electric field. All right? So recall that the potential difference between 2 points is defined as, remember we said that work done over charge, right? Potential difference is work done per unit charge. We had said that, and that was something that we said you should know. All right? And also the work done is equal to force times displacement. So those two things you are expected to know. All right? Okay. So we look at the force on a charge in an electric field. How do we want to derive an equation for the force on a charge in an electric field? So let's go through all the steps. By definition, you know this, electric field is equal to potential difference divided by separation. That was just given to you. Also, if we substitute for V, remember, V is equal to work done per unit charge. All right? Okay? So if we substitute for V, we will get that the electric field is work done times charge times distance. If we make the substitution. Maybe I should write that. All right, we have that E is equal V over D. And then we know that W is equal to work done per unit charge, right? And if I substitute for V, I will get that E is equal to work done per unit charge times 1 over D, right? Which is the same as W over QD, all right? So the next thing we do is, but again, work done is force times distance, right? And so we can now say that work done, we have that E, since work done is force times distance, I will have force times distance over charge times 1 over D, all right? So work done is force times distance, and so the D's will go out, the D's will cancel each other, and so we will have electric field is equal force per unit charge. So the electric field, the force on a charge, and so we will have that force on the charge would be equal to electric field times charge. And so this is our result here. That's our result. We have electric field is equal to force times charge, right? So hence, that is true. So the magnitude of the force on a charge in an uniform electric field of strength E is F is equal to EQ. And these are important equations as we go along. We will see how we will employ them in problem solving. All right, so we have a few equations at our disposal that we can use in order to solve questions on electric field and charges in electric fields. All right, so we'll go into some examples. But before we go into some examples, I want us to look at the units of electric field, all right? The units of electric field, of the electric field strength, all right? Okay. Now, another thing that you will notice that another thing you will notice that sometimes I'm using the term electric field and I'm using the term electric field strength kind of interchangeably. All right, what happens is that in some texts and in some texts, you would find they would use the word electric field. They would drop the term strength, all right? And so they would say the magnitude of the electric field, but really what they're speaking to is the magnitude of the electric field strength. They drop the word strength to abbreviate it. All right, but let's look at some units, all right? Let's look at some units. Now remember, if we look back, remember electric field, we had said that electric field is equal to this, V over D, all right? And we also show that electric field is F over Q, all right? Force per unit charge and voltage over distance. So this unit here, we know that the voltage is measured in volt per meter, right? So the electric field can be measured in volt per meter, and here force is measured in Newton and charge in coulomb. But are these units equivalent? Are these units equivalent? Because they are both for the same quantity electric field strength. Okay, but let's see. Let's see if we can show that a volt per meter is the same as a Newton per coulomb. All right? Okay. So here, 1 volt, the volt is a joule per coulomb. So the volt is equivalent to a joule per coulomb. So if we substitute here, we'll get the volt per meter is equivalent to a joule per coulomb meter. All right? That's what we will get. Because now on a joule, 1 joule is equivalent to a Newton meter. All right, so if we were to substitute for the joule there, we will get that the volt per meter is equivalent to a Newton meter over a coulomb meter, and the meters will go out. So 1 volt per meter is equivalent to a Newton meter. All right, that is what we have there. So the units are consistent, and so you can either use for the electric field strength the Newton per coulomb or the volt per meter. You might find sometimes in calculations and trying to get your units and balancing your units, because you would have done the balancing the units, right, on either side of the equation to make sure that the units are consistent. You may find that using a volt per meter might be more convenient in one case than using a Newton per coulomb. But just both, they are equivalent, and that is what we want to know, that using either is perfectly in order. All right, so we look at this example. It says that in a certain experiment, a negatively charged oil drop of mass 1.8 by 10 to the negative 14 kilogram is kept stationary in an electric field of magnitude 2.2 by 10 to the 5 Newton per coulomb. If the upthrust on the drop is negligible, so first of all, calculate the magnitude of the charge on the oil drop and state the direction of the electric field. All right. This question comes out of an experiment that was done by a Millikan's oil drop experiment, in which you have to suspend a drop of oil, a charged drop of oil, in an electric field. And knowing the parameters of the electric field and knowing the quantities involved, you can be able to determine the value of the charge on the drop. And then if you do that for a number of charge, you'll be able to determine the charge on an electron. All right, so that's what Millikan's oil drop experiment was all about. So this is just an extract from that experiment. All right. So first of all, example 1, let's look at the solution. For the droplet to be stationary, the sum of the upward forces and the sum of must be equal to the sum of the downward forces. There must be a balance of forces. Those forces that are tending to pull the drop up must be equal to those tending to pull the drop down, and so they must balance off if the drop is not to move neither up or down. All right? And so the downward force will be the weight, which is the mass times gravity. And the upward force, remember we said that the force is equal to charge, to electric field times charge, right? So that this downward force is mg and the upward force. So these are equal. And then if we are substitute and calculate, we substitute because remember the mass of the drop is 1.8 by 10 to the negative 14 kilograms. Gravity is 9.8 Newton per kilogram. The electric field is 2.2 by 10 to the 5 Newton per coulomb, and the charge is what we want to find. We want to find the charge on the drop, all right? So we make the rearrange and we multiply, then cross multiply, and we get Q is equal to that, and then so we get that Q is equal to 8.02 by 10 to the negative 9 coulombs, or 8.02 nanocoulombs. All right, so that's an application. And here we see we have used a principle that we have used in mechanics, because in mechanics you would have looked at that if an object is at stationary, is at rest, or moving with constant velocity, then the sum of the forces, then the resultant force on this object would be 0. All right, and that's a mechanics principle that we have brought over here. And we see that if we want to say nothing is new under the sun. So we use the same mechanics principles even though we are dealing with electrostatic phenomena. All right, so so let's look at the next thing is, it says since the charge is negative and the electric force on the charge is upward, the direction of the field is downward. If you recall, if you can recall when we were looking at when the charges were being placed in the electric field, we saw that the negative charge moved opposite to the direction of the electric field. So we had a situation like this. If I've just tried to jog your memory, because if you notice I'm having issues with the touch screen, like my finger touchy. All right, so here we had the electric field like going across like this. All right, this is the electric field. And we had said that when you place a positive charge in the electric field, then that positive charge will move in the direction of the field. All right, because the direction of the field is determined by the direction in which a positive test charge would go. So whatever the direction of the field is, that will be the direction in which the positive charge will move. So here, if we place a negative charge in the field, then opposite charge, the expectation would be that it would move in the opposite direction to the field. So this charge will experience a force that is opposite to the direction of the field. And so here in this question now, we see that the force on the charge is upwards. All right? The force on the charge is upwards and the charge is negative. So if the force on the charge is upwards, it means that the field must be downwards because the charge is negative. So the electric field, the direction of the electric field is downward. If the charge were positive, then this can't happen with a downward field. If the charge were positive, then the electric field will have to be upward. Right. If the charge were positive, then the field would have to be upward, and then that will cause this balancing to happen. All right? So that's example 1. All right. Example 2. Let's look at another example. Now, this is a kind of a schematic diagram above. Shows an electron beam welding system in which the energy of high-speed electrons is used to weld metals. Yeah, we have all kind of different welding, right? We have the acetylene, the thing with the torch and the boof, and they weld with that, where you fuse metals. And then you have the arc welding, all right, where you use the rod and electricity and so on. But this electron welding, they use an electron beam. There is also laser. You can use laser for welding because all of them generate the required heat to melt and fuse the metals together. All right, and this electron welding, it's used for precision welding. And welding, because when you weld, the seam can become porous because air bubbles get in between it and so on, right? And so you might want to do a welding in which you don't have much porosity, and it is used a lot when you're making precision type of instruments or whatever it is you're doing. And so it really consists of a high voltage anode, and this is the part that we are going to focus more on. But all of this here is just telling you about the other parts, right? And this is the metal that is going to be welded. And the red thing represents an electron beam, which is focused using a magnetic field, right? But we wouldn't get into that. But in between these two here, there is an electric field, and this accelerates the electrons, it accelerates the electron. They get up to very high speeds. Then you focus them into a very fine thing, and then they can be used now to do the welding. All right? Okay. So here is a diagram of that piece that was circled out. We have a high voltage supply that the cathode is the negative electrode and the anode is the positive electrode. So here we can think of these as being parallel plates at some separation D. All right, and so there will be a uniform electric field in between there. All right, so assuming the electric field between the cathode and anode is uniform, draw field lines to represent the field on the diagram. So you can think about if this is negative and this is positive, then remember the field goes from positive towards negative, all right? And so the field in this case would be, that was to click. The field would be upwards, all right? All right, so that the field will be going upwards. I'll have to draw this. So this is the cathode, and this is the anode. So the electric field will be like that, going upwards, all right? And we'll assume that it's uniform, all right? So the voltage across the cathode and anode is 10 kilovolts for a certain process, all right? And calculate the speed of the electrons as they pass through the hole in the anode. Assume they start from rest at the cathode. Now the electrons are produced by a process called thermoionic emission. We wouldn't get too much into that, but when we heat things, electrons escape from the surface. That's basically what it is. All right. And we'd give you a value for the charge on an electron, which is 1.6 by 10 to the negative 19 coulombs, and the mass of an electron, which is 9.1 by 10 to the negative 31 kilograms. All right? Okay, so we look at part 2. Recall that the work done by the force on an electron is equal to the kinetic energy gained by the electron. Work done equal kinetic energy gained. All right, that was something that you were supposed to know and you were asked to recall. So we can say that the work done, the force on the electron by the distance it travels would be equal to half me me is the mass of an electron, v is the speed that the electron acquires, and F is the force times the distance, the force on the electron times the distance. So let's see what goes on. But we know that the force is equal to EQ. We use Q, but in this case, for the charge on an electron, we use the common E for the charge on an electron. So we know that F is equal to E times E, so we will substitute there, and we will have that E times D is equal to that. And since E is equal to V over D, this capital E is equal to V over D, we will substitute there, and so you'll get V over D times that, and we will end up with this, that EV is equal to half MeV squared. E is the charge on the electron, V is the potential difference between the two plates, and Me is the mass of an electron. All right, and so what we'll do is we substitute and calculate, and we make the substitute charge on an electron. This is the potential difference, 10 kilovolts, 10 by 10 to the 3. And this is the mass of an electron, and V is what we want to find. We do the rearrangement, and then when we calculate, we get that V is 5.9 by 10 to the 7 meter per second squared. Meter per second. I should put in, I didn't put in my units, that's my bad. So 5.9 by 10 to the 7 meter per second. That is extremely fast, right? That is about 0.59, about 60% of the speed of light. That's really fast, all right? So these electrons have tremendous amount of energy, and they are able to penetrate, all right? So that brings us to the end of today's lesson. And so today we've been discussing charged particles and an electric field in Cape Physics. I hope you have understood the points we discussed today. We want to make sure you are understanding what is being taught. Remember to keep safe, wash your hands regularly, sanitize, and wear your mask.